using high-performance computation to conduct cultural analysis of artworks, improving wind power generation, what every president and citizen should know about physics, and new tools to track the erosion of California's coastal bluffs. But first, scientists use the unique characteristics of Iceland's hot spot to understand Earth's volcanic processes, all on this edition of On Beyond.
As one of the most volcanically active places in the world, Iceland's landscape is dotted with bubbling mud pots, exploding geysers, and fresh lava flows that ooze alongside older lava stacks, eroded by Ice Age glaciers and laced with moss. For David Hilton, a geochemist at Scripps Institution of Oceanography at UC San Diego, this rugged landscape provides an ideal vantage point to peer inside the Earth. His work on the Icelandic hot spot is advancing scientific understanding of our home planet by helping to explain the natural forces driving these incredible attractions.
Iceland is a very special place because it sits astride the mid-Atlantic ridge. So it combines a spread-in environment where new material is brought up from the mantle and spreads between two plates, and it also includes a hot spot. So this is anomalous melting of the mantle, producing very large volumes of lava, and consequently, Iceland sticks out from the ocean. It's an island, as opposed to being part of the mid-Atlantic submarine ridge. So Iceland is accessible to us. We can go there. We can study both processes which occur on the sea floor, and we can study processes associated with hotspot volcanism.
Iceland's volcanic fury is the result of both diverging tectonic plates and the simultaneous action of a stationary, fountain-like plume of material from deep inside the Earth's mantle. The geochemical signatures locked in rocks erupting from the island's 30 active volcanoes, along with geothermal fluids seeping out from below the surface, offer the scientists unprecedented access to Earth's interior as it rises to the surface at the Icelandic hot spot.
Iceland is very unusual because normally it would be part of the submarine mid-Atlantic ridge. But something is under the source of Iceland to produce so much melting such that it now is emerging over sea level. And people think that this is a hotspot. And one of the tests that we want to do is with our isotopes is to see how much primordial material is contributing to the Icelandic hotspot, and indeed really to test if this material is stored in a different part of the mantle than is normally sampled at mid-ocean ridges. Is it stored in the deeper mantle? And if it is stored in the deeper mantle, well, perhaps we do need a plume to transfer it from the deeper mantle to the surface. There are two types of samples, as I said, rocks and fluids. The rocks, we collect the rocks in the field. We break off a piece of rock, transport it back to the laboratory here at Scripps. We pick out the constituent minerals of interest, be they olivines or pyroxenes, and then we crush these minerals in a vacuum system to release the volatiles. On the other hand, when we sample the mud pots and the hot springs, we collect the fluids. We collect it with a funnel. So we use an evacuated glass bottle, and we take the gas coming from the mud pots into the gas bottle, trying to avoid air contamination. And again, we transfer the bottles back to the lab, extract the gases, purify the gases in both cases, and then let the gases into the mass spectrometer for isotopic analysis.
At the Scripps Fluids and Volatiles Lab, the team is unleashing primordial gases trapped as minerals inside Iceland's rocks. These gases will help the researchers gaze into the Earth's mantle, where they can travel through time to study early Earth and the origin of the hot spot.
We target a whole bunch of different kinds of isotopes. We target helium isotopes, neon isotopes, carbon isotopes, and nitrogen isotopes. And each isotopic system gives us different information. For example, helium isotopes is very sensitive at tracing material from the time the Earth accreted, 4.6 billion years ago. Helium-3 in particular, the rare isotope of helium, is not produced by the Earth. So any helium-3 that we have today was captured at the time the Earth was formed. So it's a very sensitive tracer of early material on Earth. In contrast, other isotope systems such as carbon and nitrogen reflect recycled material which has gone back into the mantle. So the isotopic composition of nitrogen, for example, tells us about material which was at one time at the surface of the Earth and has been subducted into the mantle and has re-emerged in the Icelandic hotspot.
But now we want to use this mass spectrometer to study nitrogen isotopes. So basically we want to measure the ratio of the nitrogen 15 to nitrogen 14. But this is not essentially straightforward because in the material that we are using, nitrogen is in fairly low concentrations. It's on the scale of parts per million. So it's fairly low concentrations. And since nitrogen is a trace gas in these samples, we need to take away all the gases which are not relevant to us in these studies. So we need to take our samples and process them through all this line here you see in front of us by taking out all the reactive gases. And once we have isolated the nitrogen by taking it through this line here, we inlet it into the mass spec where we can measure directly the ratio of the two isotopes of nitrogen.
The Scripps team will continue to analyze the samples collected in the newly developed instrument in hopes of revealing a more complete story on the planet's origins and to uncover what mechanism deep inside the Earth is driving Iceland's geological hotspot activity.
We're just at the early stage of running real samples, but this is really exciting work and has a lot of potentials in all sorts of studies that have to do with the Earth's mantle.
This has been a presentation of Scripps Institution of Oceanography at UC San Diego. To learn more about how you can support Scripps, visit us online at scripps.ucsd.edu.
Essentially what our project is doing is we're monitoring the sea cliffs in San Diego County all the way from Scripps Pier all the way up to Bachiquitos Lagoon in Encinitas. So it's about 20 kilometers of coastline, and with that there's about 70 kilometers of sea cliffs. And we come back about every 6 months. We try and do scans early in the year during about the springtime, March, April, and also during the fall, during October, November. That way we can account for seasonal differences between what happens over the summer months versus what happens over the winter months. Additionally, one of our projects that we're working on with it is called the Rapid Response Effort. So whenever we hear about a failure that occurs, we try and go out immediately to scan it, or as soon as the tide permits us to get out there. And that way we can accurately quantify how much has come off the cliff and keep track of it. So this is our setup that we have here. This right here is an iSight 4400 laser scanner. It can scan things up to about 500 meters away. So basically it shoots out a laser pulse 4,400 times a second, and based on how it reflects back and the time it takes to reflect back, it can determine coordinates and generate 3D models.
Right now we are at Black's Beach, which is just north of Scripps Institution of Oceanography. This area has extremely high cliffs. It actually has the highest cliffs in our study area. They get up to about 100 meters in some areas. So there's a lot of sediment that can fail and can come down onto the beach. I found interesting results, and there are certain areas that are hot spots where we note that there is increased tendency for erosion. And so what we've tried to do at those areas is take samples of the sediment from the beaches and from the cliffs and analyze the minerals and see if we can figure out, is there a sedimentological component that's causing this weakness, or is it increased groundwater discharge? We've also tried to correlate the data with wave energy data, precipitation data, and so we're trying to tie all these pieces together and see what the big picture is.
So yes, the electricity is going through me, through my body, down to the ground, and then coming back to the apparatus, and I'm not killed.
There's a great joy in teaching. It's one thing to know something. If there's nobody to share it with, it's not nearly as much fun. You walk into a classroom, and you get immediate reward. The students let you know right away if you're doing a good job. It's instant feedback.
Richard Muller's enthusiasm for spreading the lessons of physics beyond the science departments led the UC Berkeley professor and senior scientist at the Lawrence Berkeley National Lab to launch a course for the rest, all those non-science students who don't plan on making physics their full-time job.
I think if you dislike physics, it's not your fault. I think we teach it badly. We're frequently teaching only to the students who are going to become future physicists. We don't do that with English. We don't do that with history. We teach everybody that. We need to do that with physics too, and that's what I'm trying to do.
And he seems to be succeeding. His Physics for Future Presidents course packs in 500 students every semester and was voted Berkeley's best class by readers of the student newspaper, the Daily Cal.
Now your course is being webcast by the university throughout the world.
That's been a wonderful experience. The university asked me if I'd be willing to webcast, and I said, "What's that?" You know, and they explained it to me, and I said, "Oh, that might be useful if one of my students misses a class." So I asked my class, I said, "Would you please email me if you're using the webcast?" And I got an answer from Missouri. So the next lecture I said, "Anybody's not in Berkeley, please email me." 87 countries so far, including one from Timbuktu and from a high school student in Malaysia who is so grateful to the University of California for enabling him to get an education on things that he couldn't possibly do in his own country.
Not satisfied with teaching physics to tomorrow's world leaders, Muller wrote a book directed to today's leaders. In it, he uses everyday language to explain the science driving the world's most pressing problems: global warming, terrorism, energy, nuclear weapons and power, and space exploration.
I think there have been mistakes made in the past simply because people at the high level, not just the president, but congressmen and legislators, have not had the background they need. The president, if he or she doesn't understand the physics, then they don't know how to balance the diplomacy, the economics, the science, all these things. My feeling is it's not good enough to have a good science advisor. The president, in this case, our upcoming president, Barack Obama, needs to understand this stuff himself.
Boy, with all the things on a president's plate, can we really expect them to learn the physics behind these problems?
Absolutely, yes. Just as we expect a president to know the difference between Shiite and Sunni, the president has to know the difference between a uranium bomb and a plutonium bomb. If the president doesn't understand this, it's hard to make decisions with what to do about North Korea or what's going on in Iran.
Something almost everybody gets confused about, that's global warming and the ozone hole.
Muller spends a good portion of time in the classroom and in his book debunking many of the myths about issues like global warming.
One, you have to recognize how bad it is. And the surprising answer is that so far it hasn't been very bad. We've had about 1 degree Fahrenheit of global warming so far, none whatsoever in the last 10 years. You need to know that because otherwise you will misunderstand when people criticize global warming, they say it's not real. The reason they're saying it's not real is there hasn't been any in 10 years. But we don't expect it to happen every year. It's a gradual thing that builds up. The problem is going to be the developing world, but if they can't afford to follow our example because it's expensive technology, then it's not going to address the problem.
And I noticed in your book that one of the most important things that the president needs to consider in all of these issues have to do with the relative costs.
Yeah, some people think physics doesn't involve costs, but any physicist knows that to do an experiment, you have to bring the price down where it's affordable. The cost is central, the cost of space exploration. It costs 1/10 to do it with robots compared to humans. So there's some places where you might want to bring humans, but for the most part, if you can do 10 times as much with robots, you're much better off doing that.
Does the president's success in any of these areas depend on his understanding of the physics behind them?
I think so. Let's take an example of terrorism. The North Korean nuclear explosion was about 400 tons of TNT equivalent. That sounds like a lot, but if you realize that the one airplane going into the World Trade Center carrying 60 tons of jet fuel, when that burned, it released the energy equivalent of 900 tons of TNT. 900. It's more than twice the energy of the North Korean nuclear bomb.
His ability to explain high physics in simple terms came in handy during his 34 years as a science advisor to the Departments of Defense and Energy and NASA. But as down-to-earth as is his approach to talking science, Muller also keeps his head well above the clouds when it comes to his research in astrophysics. He studies cosmic microwaves and supernovas, among other things, work that has won him prestigious awards from the National Science Foundation and the MacArthur Foundation. He says it's the mix of research and teaching that motivates him.
I think Berkeley has a unique match of wonderful students, a great deal of freedom. I am encouraged to follow my crazy ideas and see where they lead. I can't imagine a more wonderful place to be for someone who's interested in gaining new knowledge and in spreading that knowledge.
Oh, thank you for sharing that with us.
I'm Roxanne Makashjan in Berkeley.
This is California's newest wind energy farm. 75 of these massive turbines are spread over 6,000 acres here in Rio Vista. Collectively, they're expected to generate enough energy to power 75,000 homes a year.
This project took 4 years and $300 million to complete. The project was built by Enexco, a renewable energy developer. Company representative Mark Tholke says partnering with landowners is easy.
Wind projects are compatible with farming and ranching. So in this area, the vast majority of landowners are interested and want turbines. In fact, the biggest complaint we get is, why can't I have more? Why can't you fit more on my property?
The landowners reap a royalty fee from the electricity that is generated from each of these 2-megawatt turbines.
The amount of acreage taken out of active use once the project is built is minimal. You can farm right up until the base of the turbine.
UC Davis wind engineer Kees van Dam, who designs more efficient turbines, says the energy output is robust.
52% of the power in the wind is converted into mechanical power by these rotors.
That's good because the theoretical limit is 59%.
So getting down to 52%, just a small percentage below the optimum is tremendous.
These 260-foot turbines now dot the Solano County skyline near Rio Vista. Each of the 75 towers produces 2 megawatts of power, which can provide the electrical needs of more than 75,000 homes.
California is a great wind market because of the demand for green power. However, wind energy is simply more cost-effective than solar. That is fact.
To maximize performance, Kees van Dam is working on developing lighter components.
A lighter blade will typically be less expensive. All the weight is on top of the turbine. If the blades are lighter, the top of the turbine becomes lighter. You can get away with a smaller tower, less of a foundation. The cost of the turbine starts to come down. Your cost of energy starts to come down.
Van Dam says using the wind to produce energy is often less costly than producing energy from a natural gas-fired power plant.
So that makes it very interesting, of course, for the utilities, because now you start to incorporate renewables without having a significant impact on the cost of energy.
UC Davis researchers recently designed a software program that combined one method of calculating airflow within 3 feet of the blade with another method that calculated the rotor weight beyond that distance. This helps to minimize the damage that can come from strong winds. Paul Fotenauer reporting from UC Davis.
For more information, please log on to broadcast.ucdavis.edu.
We're here at the Hyperspace Wall at Cal IT2, and we've loaded an image set of the works of painter Mark Rothko. Using software developed by the Software Studies Initiative and the Hyperspace Wall team, we're going to be exploring this set of paintings using cultural analytic techniques turning the paintings into sets of data that can be graphed, and turning those graphs into collections of paintings. First, let's take these images and let's move them over onto part of the wall's surface, and then load some graphs on the other part of the surface. These graphs all run over the years of Rothko's career from left to right, but their heights are indicated by different features of the images themselves: texture, brightness, number of shapes, saturation, and we can use them to explore trends in this painter's life and work. So let's organize this tile set that we have by one of these dimensions of data. We can sort through different axes, looking at something as simple as just the sequence of files, which we can view at different sizes, all the way down to a series of dots. And we can size all the way up to high-resolution textural images. I'm going to turn the size on this down slightly, and then I'm going to add a transparency effect. You can actually see the original dot data in the midst of the color cloud, and by mousing over any individual painting, you can pick it out of the space of color trends over the course of Rothko's career. I'm going to turn the transparency feature off now, and then size these images back down to a normal set. Now we can see the individual paintings no longer overlapping. Let's look at another axis. We can cycle through all of these various axes and perhaps arrive at one that has a particular shape or has an image like this one right here. We can see that if we size that particular image up that's standing out from the graph and choose to look at it, we can see that this one particular painting is quite unusual in Rothko's career for one or another low-level statistical reasons. Now, this doesn't mean that we have to do all of art history or all of visual analytics based on low-level mathematical statistics. But it does mean that the graph becomes an occasion to pick out an image and say, oh, this breaks the pattern, or this is typical of the pattern. Why? What's so particular about this image? The important thing about this software is that it allows me to explore transparent views. It allows me to look impressionistically at the way the data explodes into more complexity at one side of the screen and focuses off on the other. Let's go back to a tile view of looking at all of these images again. Now, this is where we started, and we can see, looking at this data, that in some ways we've become very familiar with the data set that we understood from the moment we first loaded it. In other ways, we can see that there are particular images, a highly textural purple image late in his career, or a very particular sort of semi-abstract work from his mid-period that jump out at us through particular analytic filters that we might never have picked out of the set if we had just been confronted with a light table. What's important about this is that we're thinking about paintings as aesthetic objects and data at the same time. And our interactive software is allowing us to do cultural analytics by identifying outliers, looking at typical images, and thinking about the paintings both statistically and historically.